Thanks for the invitation. It's a great pleasure for me to present our work about scale-out computing model on the massive core system. We call some massive core system. We call one is the HPC, and another one called Fabric SOC. And today we will introduce some work actually I was doing in Huawei before, and also some work I did with the Socialist. And my company called Quantum Cloud Future Technology. And today, my talk will go review some of the knowledge talk about today. The first one is HPC, so the GPU system, and the third one is the microslide system, what we call the fabric-based SOC. And then we will call why the scale-out computing model is very important in the MCS. And also we will talk about the MPI and OpenMP in the HPC, and also the memory coalescing, and also CUDA DMA in the GPU computing, and also we give some review about our architecture and our work with Socialist, and show some result. For the background, for me, I was doing the quantum calculation before in medicine, and at that time we do two things. First one, we do the simulation, especially for large-scale simulation with GLOMAX and the EMBO, and then we optimize the Fourier transfer because we want to solve the Schrodinger equation on the supercomputer. And then we found that the GPU is really good to do both the molecular dynamics and also the matrix manipulation. And later, we found that the similar system with the massive CPU cores, they can do the similar job as we do in the HPC and also in the GPU. And also, I will show some real practical example on the landed data networking. I was doing the work in Huawei and published some paper, and then we'll show our company's work in the movie production and also AI training. So if we look at the computing, like in our perspective, we have three regions. First one is PC, like a server. And then we go high density, we call it blade server. And if we go even higher, we can do the supercomputer. And if we see the system power consumption and also the number of cores, this is a relationship. And then in other way that we can increase our cores with lower power. However, the sacrifice is we can do special purpose computing like a GPU and also GPU cluster. You can see that's why the HGX is very hot in this region. If we see that from the ARM's perspective, we can see that two trends. Actually, most people talk today is about the ARM server, the Thunder X2. We are the first guy to test Thunder X2 as well. We did the test about 1 year and a half ago, 1 year ago, actually, 1 year and a half ago. And then also the ARM SOC. However, as you can see that the ARM server is something like they have the similar power as the PC or server, but have more cores. And for the ARM SOC, they have more less cores and less power. If we put it together, this region we call the microslice, or we call PCIe, or like more generally fabric-based massive core system. As well, if we put the ARM server, like ARM CPU together, we can call it microslice of ARM CPU, or high density ARM CPU. It's similar to the blade server, but have more cores. And another one is ARM SoC. We'll do some work both on these two regions because we have the test bed from the Gigabytes with the Thunder X2, and also we have test bed from Ampere and also the test bed from Socialist. So if we see more closely to this diagram, actually we see another trend that from like 12 years ago, each 6 years, we can see that the intra-CPU cores becomes much higher because of Thunder X2, right? We have like 48 cores. And however, that the inter-CPU connection didn't change that much. Mostly we have the caudal motherboard. And then for the class scaling, actually, you can see we can scale almost like 100,000 cores. So that means actually for the scale out algorithm, the data communication is very important. But we will even see very closely about what happened in the data architecture. You can see if we have two systems, when the data pass from one core to another core, they have a really hierarchy hierarchical structure. For example, that the green ones we call I/O, the red ones we call storage or cache. Actually, red means slow, green means fast. Connection is always not a problem, but storage is a problem. So, and this structure actually is a fundamental, the method people want to solve the traditional computer architecture problem, like the bottleneck. Then this is a diagram how we can see data transfer from one core to another core. So in order to increase the scalability and also the scale out, we have several levels of optimization. First one, we call infrastructure level, parallelization. Second one is OS level, and then third one, most important one is algorithm ones. And accordingly, we have several tools like techniques we are using. Actually, this is all the tools and techniques I'm using in my previous research and also our work. For example, actually people mentioned that in our auto talk as well, like the fast cache, like how to manage my cache. This is most of all the CPU guys that are doing. They balance how many cache or what's the speed of cache we need to use. And then what is the cache prefetch? And how about to the vector processing, the SIMD or AVX? And also we can do like big data. We can do the heterogeneous computing. We can do the GPU and the FPGA. Even today, Intel is doing the big data. And the third one is OS level. We can do the big RAM. We can do the virtual RAM, a big RAM page, and we can avoid content switching and with the TLB and the cache conscious algorithm. And the third one is a higher level with the batch. We can share laughing. We can status computing. So we predict that in the future, actually, a lot of innovation will come from the consolidation, because we have too many layers. And right now, the network is really fast. The memory is fast, and the cache, is very expensive. Then people may have some like a consolidation to do like a new for the chip design and also for the system optimization, especially us because we are doing the system optimization. So maybe in the future, we won't be surprised that people will do the I/O consolidation, like networking, and the bus, like fabrics, they will be the same. And storage, consolidation, memory cache, they will be the same. Actually, today, Intel is trying to push to merge these two, the memory and the cache. And because I was working for Huawei and Cisco before, and I see networking is too complicated. Networking is very complicated. But the circuit bus and also the CPU fabric is very simple. So can we simplify networking and to make it fast? That is actually our algorithm is doing. So of course, about scalability, it always comes to one thing that we cannot. That's a boundary. That's the sky. So because of the code itself. So this is actually one. How can we make it fast? And the problem that how can we mimic the code we need to share between each node. So this is what we test today with the SocialNext, and our group relation is a very good partner with us, and they have a system like they call it PCIe Fabric. I mean, they're not the first guy to do that, but they are the first guy giving me the testbed. So I'm doing this testbed for them, and then they have like 700 cores in this small chassis. It's surprisingly, they can control the TPD is only like 700 watts. This is very surprising. If we and also another one that they made a really good effort about it. They can do the core-to-core, CPU-to-CPU connect. The connection is about like 36 microseconds latency, and with about 10 gigabit per second the transaction speed. This is about like a 4 PCIe name. And if we see that's a watts per core, we can see compared to the ARM SOC and Intel CPU and GPU, you can see surprisingly, for the total system, not just for the CPU itself, for the total system, this system is really good. It's about 1. That means each core only costs like 1 watt to drive the system. If we see that the GPU system, with the CPU into account, it actually is about like 1/3, about 1. 1/3. That means it even sees the efficiency based on this number. This system can be about only like 3 times more power than the GPU system. But as I said, This is very general purpose system. We can optimize the code easier than the GPU. So from this this table, we can predict the performance will be good. Then how to make the performance good is a question. Especially when we have 700 cores, how can we make it faster? Then we did all this architecture. Actually, we didn't overstack. We only see that overstack is supported by Linera, so we didn't do that because it's too heavy for us. We did PBS. Of course, PBS is what I did before, so no problem. It's very fast, and it's batch. It actually is a process, so it's very fast, very flexible. You can do whatever you can do. Normally we run with MPI, and if you want to do some more trick with OpenMP, you can do the inter-core optimization. However, no isolation, and it's almost for like scientific calculation. Yeah, I was going to do like GROMAX sense here, but because of a lot of people doing GROMAX and AMBO on on the ARM system already, so we just drop it. And then Kubernetes and the methods is the one we want, especially for the container. So all the things we're doing is container-based. So we want to use everything with container-based because first one, they can software define the hardware. We do not need to optimize the driver for all the board for each application we want to do. We just optimize the container once. Second one, it's very fast, and reasonably it's good, and also it's production ready. And then we can do something like we can put our application into the container, and easier for us to transfer from one testbed to another testbed. So this is our architecture. Our architecture is called shell nothing with message queue. So why we put this together? Of course, shell nothing because we want to increase the scalability. We can increase the scalability always like linear to all the loads we added into the system. And then in order to make the state shared among the cluster, and then we propose two things. First one is the message queue. This one is the one we can management the task, like the time order. Second one, we have a storage, central storage. As I said, because the connection is about 10 gigabits per second, it's very fast. So it's not a big problem for SOC to read from local or read from the website, from the remote, that's the thing. And also, even we want to increase the read, the write, we have one container called IO core. This will do the DMA to read the data we want to read. So how to do that? Actually, it's very simple as well, because the queue here, some core will read the data in advance. You can see this mimics the prefetch. To prefetch the calculation from the cluster. So actually, you can see from this architecture, we call it stateless. Actually, we mimic all the chip design architecture into our software architecture. We can make really fast. Okay, this is our example, one example. This is old work, it's published, so I can say that. So this is one example that we applied our architecture into the GPU computing. We use the DBDK to speed up the I/O, and then with the GPU, because this is really old work, as I said, from the scientific version that I did in the US. Yeah, and with one GTX 480, it's about like 4 years ago. No, it's about like 6 years ago before I started my company. And then we can reach, even for like a 148 at that time, we can reach, you do some optimization, we can do even faster than the some 590. 590 is double of the actually 590 is almost like double as the 480. And the reason we can do that, we call ASM, Active Shared Memory Management. Active means that we have some WAP to prefetch the data from the global memory, from the GPU to the shared memory. And then when the WAP, the real cores can do the computing, they will see, oh, my data is here already. So we do the overlapping. And then we tried our work to do the rendering. Yeah, rendering is one of the computing intensive work and the real for the production, like cinema quality. This is the work actually we do compared to the X, like 1.5 years ago, compared to the Intel E5. And not surprisingly, as I said, when we do some tests, first we want to see the architecture. So SunX is really good because the bandwidth is good. We work with gigabytes at that time. We bought a server. I mean, I don't know why we need to buy a testbed, but the reality is pretty good. In some cases, especially for parallel case, the performance is about 3 times from the SunX2 system compared to the E5. If we do some more like optimization with container, we can even achieve something like 5 times faster. So this for the cinema quality computing, the ARM server with container optimization, they can be really fast in the SunX2. However, then today, and actually last week and last month, we did the same thing for the SOC system. Unsurprisingly, the SOC is really bad, right? Because of it's SOC. So this is the comparison between the E5 and the SunX2 and the SOC. However, for the absolute performance is bad. SunX2 is good because of the memory bandwidth. However, if we scale the result with the cores and the frequencies for each chip, you can see Intel is better than everyone. So if we see that we scale the performance, like it's good to everyone. But if we scale again with the what, like the power to power the power consumption to power this result, the SOC is really good. Unsurprisingly, because I said as ARM SOC is very power efficiency. Now this is one result we did, and with rendering, like a cinema rendering, okay? It's not like a cell phone rendering. It's for the cinema quality, like a post-production rendering. And then we try to say, hey, how about AI? Can we do the AI? And then we do cafe. We do compile. This result is not good, this is SunX2, yeah. And this is GTX 1070. We didn't use the most advanced one because the result difference is too bad, yeah. So we scaled the result, it's not good. And then we almost dropped our calculation on the AI. Then we use SOC to do that. Unsurprisingly, for the cafe and the darknet is really light. You can see Intel is really good. However, if we scale like again with the cores and the CPUs, you can see SOC is good. It's not bad. So we do the both training and inference. You can see SOC is good. So this gives our some idea that if we compete with the raw performance, I think SunX2 is good in some cases like rendering. But if we can compare that the scale, like consider the power and the cost into account, the SOC is good. So we think that in the future, the fabric-based SOC will be a really good solution to the both edge computing and also the cloud computing. And I think from the result we did, we think that maybe we can think about more time to link the small cores together and make the performance faster instead of like just make faster CPUs. But of course, because we are a system company, we like to optimize the cores and also the chip with the application we have. So that is what I want to say. Thank you. Yeah. This is the result. I think very surprised. Surprised us a lot. Originally the first time when we talked to Peter, we want to test ARM server. The gigabytes to us, I think 1 year ago, 1 year and a half ago, and then they sell out a box, SunX2. And then we do the result. As I said, because of the bandwidth is really good. So this is a server-based CPU. The performance, of course, is good because of the bandwidth. And then the SoC is only 5 watts. Actually, it's more like a cell phone CPU made by SocialNext. And when they come to me about 2 years ago, they talk about that they are make a system with like a fabric-based, blah, 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 blah. I said, okay, I think it's good because we do the calculation actually we do the calculation for this table the first time. Yeah, this is the one, when we see some system, we'll calculate this first. When we see this, we know that, okay, approximately, if you have a really good optimization technology, you can make the performance from this. And unfortunately, we are a company, we can do the optimization very well. So we see this, and then we say, oh, then they can do this. Then 2 years ago, they delivered the box to us. Yes. So They are both ARM-based, but one is for server, one is for SOC-based. So the power is much lower. And then we do some calculation. Yeah.
I think this topic is very interesting. So talking about the fabric, so um, you mentioned the PCI fabric you are using for your solution. So do you have some comparison with the NVLink from NVIDIA or Infinity Fabric from AMD?
Good. Very good. Actually, the question is really good. I cannot talk too much because some confidential information, but I can see this picture is more clear for what I talk about. You know, when we connect two cores together and two CPUs together, we have different connections. We don't talk about cache one because it's inside the core. We can talk like a socket. We have like a dual socket, like quad socket, right? And we use a QPI, and we can use like networking. So if we think about what is QPI, actually QPI and PCIe are the same. The fundamental are the same. So right now, people try to optimize this part. You can use the IB, like when I was in school, I was using IB, and then people use PCIe, and people use like another connection, like HP. They use just the internet. So why we choose, not me actually, yeah. Why SocialNet choose PCIe? The reason they gave to me is that because PCIe has lower latency, and also it's very fast. Yes, that's why I choose the PCIe. And they did some calculation. I didn't ask the result because I know the result because PCIe is good. Because PCIe and the socket best, that's the same, yeah.
Maybe the PCIe 4.0 can also be helpful here.
They use they use 2.0 because when they developed the system, it's about like 3 to 4 years ago.
Okay.
Yeah, right now if you use 4.0, you can do 4.0 here. You can increase a lot. However, use 4.0, you need to optimize your buffer very carefully. Otherwise, you cannot reach the performance you want. Yeah.
Okay, so there should be some balance, right?
Yes, that balance between latency and the buffer.
Okay.
The PCIe buffer is an issue. Yeah, you need to optimize that. Yeah.
Okay, thank you.